All right, we're back with another project here. We have a three tier design here of the core distribution and axis layers. This design right here is mainly to tie up everything that we talked about the last few. Um, right here, you don't understand what this really is. So essentially, the orange one right here is the core layer. This is essentially the backbone of the whole entire uh the whole entire project in the sense where it's meant to it's meant for to move traffic as fast as possible, but also focus on like redundancy, high reliability, low latency, and just moves traffic as fast as possible. It's like I would say it's like the barrier for you to be talking to the internet, and the barrier for you to be talking to the internet, and then um yeah, basically the barrier for you to be talking to the internet. Um, and your access way to be talking to the internet, right? So I actually have my config here. The other next layer is the distribution layer. This is essentially where is the decision making. I would say since it routes between it's routing traffic between each other. There's redundancy and there's failover. So as you can see here, we have two layer 3 switches per stack here, right? Because we have two more layer 3 switches in the core layer. We have two more sets here, three sets in total, with them both interconnected to each other. So if one goes down, the traffic can go to the other one, stuff like that, right? And then the access layer is where all our end devices connect. So for here, we have just layer 2 switches and also a regular PC for this design. But if you could do laptops, phones, and wherever it really needs to get an IP address or just need to talk to the internet, just there, right? So I have my config right here. And I'm just gonna basically explain everything as down here, right? So we have LADP running and on all these switches, all these layer 3 switches and stuff, right? And we also have this password encryption. So just to explain, right? Not encrypt, enable secret class, right? Enable secret class is basically allowing you to set a password to the privilege exec mode, which if I had to explain, right? Uh, this is actually the password. Oh, okay, so this one, this is actually before, right? But Cisco, yeah, Cisco. So this one is specifically for after you type enable, right? So where you actually can start doing the configurations, because the first mode is the user mode. In that mode, you're not gonna be able to do anything. But if you wanted to actually mess with the router, usually where you have to go to. Neo secret class allows you to set secret class allows you to do it. Well, it's enable secret. That's actually the function. Class is actually the password for it. Line console is basically the configuration mode for the console port, and then this one right we have password Cisco. So remember, the console port is actually the physical port of like the device. Uh, and all of these like layer routers, layer 3 switches, there's a port which is the console port that allows you to physically talk to it, but which you would need to be physically there to actually connect to, right? Um, I will actually explain this in a little bit, but this is actually for a one of common fault cases where, in a sense, let's say someone is locked up from the device and they can't access it, or let's say network engineers can't access it. Someone would have to go in person to actually be able to talk to it. This is like the automatic way. The console port. You need to physically go to there and connect to it, and you can manually configure it from there, right? Basically, console 0 is for that, right? VTY, which is virtual terminal lines, these are used for remote access. So talking about that analogy, so let's say you're you're at home, right? You're working from home, right? Uh The remote VTY is specifically for remote access. So Telnet, SSH, don't know what those are. Those don't know what so if you don't know what those are, both of these protocols are for remote access. So it allows you to actually talk to the machine while you're away. It allows you to actually do it really do it as long as you have it right. Telnet is a older protocol where it's actually unsecured. They both do. Well, I would say Telnet and SSH. They both do the same thing. Just know that Telnet is an unencrypted way of doing it. So like any commands you do, like show run, show IP interface brief, show VLAN, show many show spanning tree. Those commands. It's gonna be if someone, for instance, a bad actor was actually looking at it. Uh, they could see everything. They would be able to see everything. As compared to like SSH, which is it's port 22, right? TCP. Uh, it's actually encrypted. Everything you have that is typing is completely encrypted. No one's gonna be right. So BTY basically allows us to do this, right? And basically 04 means the sessions that are met through it, and basically password login, which login requires the password, requires authentication with the password for remote connection, and then exit obviously just config, and then server's password encryption. It basically encrypts the passwords that are here, because these passwords here, because Cisco class, these are plain text. You would be able to see them. But if I do show run in this layer 3 switch, right, as you can see, uh, they're not readable. Like, I don't know what old 22455 DOA16 is, right? But essentially, it basically prevents casual viewing of like what the password is, right? And this is not, and I believe because I did a little bit. This is not like heavily encrypted. This is not heavily encrypted at all, right? I'm pretty sure this is weak encryption, but for the sake of this lab, right, we're just to hide it, all right, just to put a mask over it. But essentially, that's really about it. And this is really done on the core layer, because this is like again the backbone, the thing that we actually care about. You can just put this on all the other distribution layer switches as well, but essentially that's for this part, right? If you don't understand what how they even do all of this, how, right? So essentially, we have 5 VLANs here. So we have VLAN 10 named staff, VLAN 20, VLAN 30 admin, VLAN 90 servers, and VLAN 99 management. We have both, and we have these basically done on all the access switches. And we have we're configuring access ports and trunks to the distribution layers, right? So for instance, this one right here, right? Int range FA01 fast internet 1 that through 2, switch port mode access, switch port access VLAN 10. So essentially we're pointing these computers in VLAN 10, and then it enables standard tree port fast, which I will talk about right. Um, and then on the exit switch, basically we have I'm literally doing this after I have done this like a couple of days ago, so I'm kind of like trying to remember what I did here. 1020. I feel like I feel like that's a typo, because I don't think that's supposed to be 20. It's supposed to be 102. But essentially, the port. Oh, it is a typo. I see. This is why I actually catch my mistakes. It's actually supposed to be -2. So basically, for this switch, it's going to be 1 and that 2 gig interfaces, right? We have this. We have these set as trunk ports, and we're basically allowing these. And we're doing this for each of these access switches. And between this, we have spanning tree, right? So spanning tree, if you guys already don't know what this is, it's just prevent routing loops. That's the whole idea of spanning tree. Rapid PVST, which is rapid per VLAN spending tree. This one, right, is Cisco's proprietary version of it. Is actually a proprietary version of STP, but essentially, rapid spending tree uh is running a separate instance of STP for each. Hence why it's per VLAN, right? And it's actually a much faster version of STP because STP is actually slow. If I remember correctly. Um, this is about like I think STP is like 30 to 50 seconds for converging. Rapid STP does it in seconds. And this is only exclusive to Cisco. And I believe there's actually one that does it for regular switches. Like if you were to do it for Arista and Juniper switches, if like not branded for obviously Cisco, then yeah, I believe there's a protocol that does that. I'm not getting my, I'm not remembering from the top of my head. But again, RS rapid PVST is essentially is what is basically improving STP, making it much faster at the topology chain. Really, it right? And all of these switches here have it for the core switches, right? S1 and S2, because I actually have the name S1 and S2. You can't really see it because the interfaces, but no, this is S. The first one. This is the second one. I actually have the spanning tree on here with the root primary for each. So I actually have a document here on the right side that actually kind of explains it, but because I'm basically doing it based on right. So basically, the first uh the root bridge or the primary root. So basically, this is like where all of the VLAN connections is done, right? This is the first like line of defense, and then the other switch is like or failover. So like this switch dies, it still could talk to this one. It'll just automatically take over its place, right? So for the first one, we have 10, 30, and 90 as being primary, and the other one being 20, 90, 20 and 99. So for both of them, and then we just flipped it, right? So the other one will be 2099 as being primary and 3090 as the secondary. So again, and remember, this is for the case of redundancy. So like if one of these go down, and immediately switches to the other one. And the idea is that both of these layer 3 switches on the core layer essentially handle this traffic, or essentially handle both all these VLANs all together, right? But you're basically segmenting it. I would, in a sense, I would say low balancing it, but yeah, that's basically for this part right here. We have obviously internal VLAN routing done here. Uh, based off these VLANs, I'm using the 10.10 for VLAN 10, for the subnet, 10.20 for this subnet, 10.30 for this whole, well, I should say broadcast. 10.30 for this broadcast, and a 10.90 for this broadcast, a 10.99 for this broadcast. Just keep it simple. For /24, right? And I actually have it right here, but it's kind of zoomed out, so you might not be. Um, uh, and for the core layer switches, basically, well, the switching layers are basically the first address, and then the core layer switches have the second address, right? Uh, and uh, and we also, you can see here, we also have a server here. This server here has it set into the 30, I think it's set to VLAN 30 for specifically for admin in this case, and we have it on switchboard access VLAN 30 and port fast. I don't remember what port was, but actually, um, I believe port fast, if I remember correctly, just completely skips over like certain phases because this is obviously for STP there's like listening phase, forwarding, or no, listening, learning, and then forwarding phase. Port fast just immediately goes straight to that with no questions asked. Like it just skips throughout that process, right? That's what port fast is. If you're wondering what this right. Let's see. We have also the OSPF here. We have OSPF running on both of these core switches and in the router, right? And we have them with the respective IP addresses. Uh, I'm using 10.255.255.0/30 and 255.255.4/30. These are for the point-to-point links to the core switch, and from the core switch to the core router, right? So this one right here, if I could actually hover over it, uh, yeah, right here. So it's gonna probably be hard for you to see, but essentially, just 1020, which is the one that's connected to the router, it has a 10.1. Well, it's dot one, 10.255.255.1, right? And then this router has it as 2. Enable. Let's go again. Let's go run. Right. This one has it as dot 2, and then for the other link it's dot 6, which with it beginning at 5. Right. Dot 4 is the broadcast. Dot 0 is again the broadcast, or the network. I meant. Right. So it's specifically the network. Right. Um. Yeah. Go back to the note. Yeah. So that's for this. OSPF done right here. This is right here, just configuring the interface, and then right here we're just doing all the routes to it. Essentially, we have R1 talking to both of these, so they have them both as peers, as you can see, right? We have both of them as peers, and obviously there's 2 layer 3 switches, of course, in the core layer. So we should see 2, and they're both in full state, meaning they're actively. So, and then for the other switches, right? So between these two, I basically have all the VLANs routed into each other, routed to each other. So this is for both of them, and I also have the ones for the respective one to connect to the router. So for here, I do show OSPF, and you see there's the one that's connected to the other layer 3 switch, and then just all the ones for. Yeah. So there's that. Let's go. Not only that, we also do have DHCP running here. DHCP is, I believe, where is this run? I believe it should be running on. Yeah, DHCP is running on. Pretty sure. Yeah. So DHCP is being ran for 10. It's being ran for staff, admin, and IT. So 10, 20, and 30. That's where you have goals for them, and for the layer 2 switches, again, we had IP helper addresses for each helper addresses, so they know what the DHCP is, and it will basically forward that request to the router, right? So basically, we had DHCP running for the VLANs, right? DNS server that's at the 8. This is basically actually as a relay, right? And we have the excluding addresses here. And finally, we do have that. Right. So, let me zoom out. Right. So this one we have it. So this is supposed to emulate the internet ISP. All right. So we have it connected to the cloud here, to the modem, and to another router, right? Which, because remember, everything's connected to each other. And it's connected to. It's most likely connected to a router because remember, routers route traffic networks, right? We have that. We're using the address of 203.0.113.1, or that being the address. This one is one, and this one be. This doesn't have any configs, but or well, it does have a config, but it doesn't have any like security measures. Dot two as being the other address, and we actually can ping it for in this. We have to wait. No, not even configuration mode. That one. That too. Successful. So we move this to the right. Go to simulation mode, and yeah, go to simulation. I'm gonna redo it. He's able to talk to it. SDP is running around here. So that's um that's that. If you guys don't know what NAT is, it's basically network address translation. So to explain it, right? So basically to explain it, right? NAT network address translation translates one IP address to another, right? That's literally what it is. The reason why we have NAT is we for this in this case we're using IPv4. IPv4 addresses, right? Back then, IPv4 addresses, well, founders at that time thought that we had enough addresses for the network or for the internet, and we actually ran out of these addresses. And I will talk about this probably in the future about IPv6, because that's the newer version of it, which is way longer address, but we have like limitless addresses available. We have ran out of IPv4 addresses. So in a way to combat this, and this is actually I would say this is actually like a more temporary workaround, because IPv6 I think is the actual solution to this problem. And that essentially translates one IP address to another, right? And then basically conserves that IP address. So it basically has a private IP mapped to a public IP, right? PAT or PAT, which is actually running on this. PAT essentially is a type of NAT that allows many devices to share one public IP address, but in a sense, it does it by ports, right? It does it by the IP address to the port. If I'm so we have NAT right here. I have basically in order for NAT to be applied, we have to create an access list, and access list. I do have a permit of basically any words to be translated, right? And wildcard mask right here. Then IP NAT inside source list. This is the number. Source list one interface, which is this interface F0, and overload, which is the name for people. So, really, I'm trying to remember what it was, or to show NAT. Yeah, it should be show IP. Uh, Translations. Oh, we don't have any addresses. So, I'm going to actually. So this the so this one has actually one, right. I'm going to go and I think other. First one's gonna fill because of ARP. There you go. And if I do it again, I should be able to. All right. So basically, like the inside global here, right? It's a public IP that's actually being seen outside, and that local one, obviously, network, the private IP. So this is hence why this is all IP addresses. And then this is the outside local. It's basically the device that's seen on our network, and then the outside global is actually in the real world, right? So, and you can see that with the colon right here, they have port numbers. Uh, This one is one. Typically, you would actually see the actual port number. So, for example, ICMP doesn't have a actual port number, right? But like, let's say we had HTTP, for example, like port 80. That would be an example. Um, for this case, obviously, it's I'm also not the case, but that's for really about NAT here. Um, so again, we have the code here. So I do have the interface configured here. IP NAT outside, IP route to it because I have a static route to it, the switch or to the not this other router, right? And then the access list one this basically any address. And remember that if you don't know what this is, basically saying any traffic that sent to this router just to the other router, right? And then or we have on this one, really this is for the R1 or the core router. Is so this is for the core router. This is basically 8 and 9 as being inside and then FA0 outside. And then we're applying that interface. Yeah, that's about it. That's pretty much about it about this whole lab. This whole 27 minutes.